So let's take a look at the 2 degree of freedom planar robot, and specifically applying the Denavit Hartenberg scheme to finding out its end effector position relative to our base coordinate system. So first, let's just kind of draw a little sketch, right? We're going to have our ground here. This is our fixed object, not really going to be moving. This is what we're attached to. And normally this has some sort of indication of where your base frame is at. And we've got a linkage here, and there's another joint, and another linkage here. We've got a point, and that's just going to be the point of our end effector. So we call it planar because even though there's 2 degrees of freedom, and they're still hooked in the x-y axes. So even if we added another on the scheme, another linkage, it could still be planar. Even if it's 3 degrees of freedom, it could still be constrained to 2 dimensions. So let's start off by taking a look at just going through the procedure. So the first thing is we're just going to kind of number these, right? So say 0, and here's our 2. So these are kind of our reference frames. So the first thing we need to do is assign a z-axis. And so in this case, the z-axis is actually what's coming out of the page, right? Because it's 2-dimensional. So we're just going to say that for all of these guys, the z-axis is sticking up, like towards you. And that's where it's at. And the reason is we need to, our procedure says that our z-axes need to be where our rotation is about. And so in this case, the rotation of z, or 0, is about z, and the rotation of 1 is also about z. So that's why it's fair to just have all of our z-axes pointing up. And really, for the most part, for this specific problem, they're not going to be used much. All right, and our next thing is to declare our base frame, or O0, right, our origin 0. And so it probably makes most sense just to put that right here. This is x0 and y0. And now it's time to do the rest of our joints. So we're going to just kind of start incrementing upwards. And so there's a few rules, but this one specifically, and for most of these, is actually kind of intuitive how to go about placing it. Dash lines don't turn out that well. But this one here, so this is our x1, y1, and then here, this is our x2, y2. So we've got these two, really these are the two that we're really looking at, is 1 and 2. These are the 2 joints that we're really focused on. Even though this isn't a joint, these are the 2 transformations that we really want to look at. And so the first thing, or not, I guess we're well past the first thing, but the next thing we need to do is make a table of our 4 DH parameters. So how we do that is we're just going to say, make some titles here. So we got link. That's our link number. So we've got, remember I said we're only looking at 1 and 2 because 0 is fixed. We're assuming 0 is fixed and 1 moves relative to 0. So even though the movement is at 0, 1 is relative to 0, and 0 is always fixed. What else can we have? Well, we can have r sub I. We can have alpha sub I, c I, and theta I. So we don't really have any links for this specific design, so we're just going to say they pretty much are what their variables are. So in this case, how about a nice green here? So r sub 1 is just this length right here. So this is r1. And that's what it is. It's just called r1. If we had some units on there, if we had a value, we would obviously throw that in there. And so no surprise, this length right here is r sub 2. Got r sub 2. And alpha has to do with the angles between the z-axes, in which case all these z-axes are pointing in the same exact direction. So that means that the angle between them is just 0. And this di value, this has to do with the offset compared to the x-axis. So if this arm was like an L shape, if this joint was an L shape, we would have a value there. But in this case, we don't. Okay, so this is 0 and a 0. And then our theta values, we just know from kind of doing this problem before that this is theta 1, then this is theta 2. And so those, once again, they're just they're variable names, right? Theta 1, theta 2. We should remember, right, it's kind of a critical thing. These guys are the variables, right? This is a variable, this is a variable. So sometimes you might actually denote that with an asterisk on there, but we're going to be writing these variables a lot, so we don't want to have to do that. So we've got all of our stuff kind of declared, and after we've got our table, it's really just declaring our homogeneous transformation matrices and then multiplying them together. So let's first look at the homogeneous transformation matrix for A1. So A1, or of A1, not for A1. I guess it's for joint 1. Kind of a big matrix here. And what we can do is we've got a standard form for this, which is given to you in the notes. And so we just kind of take these values and substitute them into that standard form. So the first one is just the cosine of theta I, or in our case, theta 1, so we're doing A1. And we've got a special notation for that. If we're doing a cosine, we just say C, right? And that's cosine, and then a subscript of theta. That's the cosine of theta 1. And then the next one is negative sine theta 1 cosine alpha 1. And alpha 1 is a 0, and the cosine of 0 is just 1. So it's kind of like we don't have to put that on there. We can just assume it's a 1. Because this alpha is not variable. We're not moving. We're not kind of rotating out of the page anywhere. So that means that we can just put negative sine. And the next one, so we don't have, we have the sine of alpha 1 in this term, and the sine of 0 is 0. So that means this whole term just goes to 0. All right. Now we should be doing r1 cosine of theta 1. And so those are all valid things, so we'll just write it as they are, right? r1 cosine theta 1. So there's our first row. Now our next row, sine of theta 1. Nothing else we can do there. And then we have cosine theta 1, cosine alpha 1. Alpha 1 is 0. That once again is a 1. So that means we're just left with cosine theta 1. And for this term here, we've got a sine of alpha 1 again, which is a 0, so that means this whole term goes to 0. And then here, this is just r1 sine of theta 1. So r1 sine theta 1. And now this spot right here is always a 0. Always a 0, so we just put a 0 there. Then we have the sine of alpha 1, and the sine of alpha 1, well, alpha 1 is a 0, so that just goes to 0. And then the cosine of alpha 1, that comes out to a 1. Cosine of 0 is a 1. And this is always just d sub I, which in our case is d1. And then we have our bottom row, which is always, always, always just 0, 0, 0. And this bottom row is here so everything multiplies properly, right? We want to have 4 by 4 all the way around so everything's nice and symmetric. That's A1, and we're just kind of looking at that table to get these. That table and our standard form for our homogeneous transformation matrix. So now let's look at A2. Bracket's a little bit bigger this time. Case. And we're just going to kind of be plugging some stuff in here. And it's going to be, well, no surprise, this joint to this joint, right? So joint 1 to joint 2 is the same as joint 2 to joint 1. So it's going to be the same as A1, except for instead of theta 1s and R1s and D1s, we're going to have theta 2s, R2s, and D2s. Oh, we have an R2D2. Anyway, so we can just kind of copy this guy's form here. So we got a cosine theta 2, and we can do this because alpha and D, these guys are also zeros. So I guess we don't even have to have D1 there, right? This could be a 0. All right, so let's just kind of do the busy work here. R2 cosine of theta 2 sine theta 2 cosine theta 2 0 R2 sine theta 2. We've got a 0 0 1 0 again. Remember that's a 0. And our standard format here is 0 0 0. Always that bottom row is going to look like that. So now we've got A1 and A2. So we've got both of our homogeneous transformation matrices. So now if we want to figure out the position of 2 relative to 0, well, we can kind of start linking our stuff together. So we've got what we're looking at is we want to be in 0. I want to find the position of 2. Looking for this transformation matrix. So that just equals A1 times A2. So I highly recommend looking up how to do matrix multiplication, or practicing with a tool to get good at doing it. However you want to do it. I think that knowing some of the background behind it is definitely a good way to go about things. So remember, the multiplication works by taking this element times this element plus this element times this element plus this element times this element plus this element times this element. And that gets you just this top corner element. So you've got to do a lot of operations for a 4 by 4 matrix. So once again, what we've really got here, figure out this first element. we've got cosine theta 1 times cosine theta 2. And then we're adding on negative sine theta 1 times sine theta 2. Negative sine theta 1 times sine theta 2. And then we've got two zeros here, so that's going to be plus a 0, plus a 0. And here's where things are going to kind of be a little taxing, but hopefully we'll start to notice trends. And that is, we've got some trig stuff going on here. We've got cosine theta 1 times cosine theta 2 plus negative, or I guess we could say minus sine theta 1 times sine theta 2. And as it turns out, this actually simplifies to the cosine of theta 1 plus theta 2. So those two angles added together. So it's kind of looking at some of these trig identities and remembering them or having a way to readily access them is definitely a good idea to kind of simplify these guys. So that's two things. I would really look back at your trig identities and also matrix multiplication. Now I'm just gonna go through and write what this matrix looks like in its final form. So we've got the cosine of theta 1 plus theta 2, and this next term is negative sine theta 1 plus theta 2. We got a 0 here, no surprise. And we've got next term alpha 1. Oh, sorry, this should be R1 cosine theta 1 plus R2 cosine, oops, my line, I'm gonna go a little bit over my line there. This is cosine theta 1 plus theta 2. So this is the cosine of both these angles added together. In our next row, we've got sine theta 1 plus theta 2 cosine theta 1 plus theta 2, 0. Got R1 sine theta 1 plus R2 sine theta 1 plus theta 2. And then we're left with actually a 0, 0, 1, 0, 0, 0, 0, 1. So no matter how many times we multiply these guys together, we're always going to end up with our final row of 0, 0, 0, 1. This is kind of because we have no alpha components and nothing really going on with our z-axes. So that's why it's kind of stuck like that. So this is our kind of our final thing here. And we can't use this just alone or as it is to figure out where 0.2 is relative to 0. But what we can do is we can dissect this, and we can actually find that. Actually, here, let's change my color. We're kind of doing a little special thing here. So this part is the rotation matrix, and this part is the translation matrix. So, and what's nice is we don't have, this point is at the origin of this coordinate system, so we don't have any offset. That actually means that we don't really have to use this translation thing to figure out where x2, y2 is at, we can just use the translation to figure out where x2 is relative, or x2, y2 is relative to 0. And also, no surprise, we don't have anything in the z, right? There's no translation, meaning that we can't go up on the z here, and we're also not going up on the z here at all. So I would consider this kind of to be our finished final form to figure out how to get where x2, y2 is relative to 0 as a function of the arm lengths and the angles at each joint.